Hashing. It takes a piece of data and turns it into a fixed length string of random characters and numbers. It does this regardless of the size of the data. For example, the MD5 hash of this famous code by Sun Tzu and this entire Ubuntu x64 ISO file will both be 128 bits long, where one is only a couple of bytes in size and the other a couple of gigabytes. It has a wide range of real-world applications. For example, it's often used to encrypt sensitive information before storing them into the database, to protect them against unauthorized access. You see, contrary to popular beliefs, hashing is a one-way function. Once the data has been hashed, there is no way to extract the data back from the resulting hash. So, even if someone gets their hands on it, there is no way for them to access the data. It's a part of programming that's often taken for granted, and yet people rarely understand how it really works. In this video, we'll take a deep dive into the inner workings of one such hashing algorithm, MD5. When you hash something, the resulting hash will always be the same, every single time. So, what's really going on? Well, if we look under the hood, we'll find these complex sets of operations that makes up the MD5 algorithm. Let's start with the M block. This block represents the main input data. Let's use another one of Sun Tzu's quotes as an example. First, we need to convert this string into its binary equivalent using the ASCII to binary table. After converting, it has a length of 360 bits. According to the MD5 RFC, for the algorithm to work, the data block needs to be at least 512 bits long. In cases where the input is smaller than 512 bits, we need to add something called padding. Padding is basically a 1 followed by a bunch of zeros. But that's not all. The final 64 bits of the block are a bit special. These are used to represent the length of our original input before padding. In our case, it was 360 bits, so it will say 360 in binary. With this, the total size of our input data is 512 bits. Let's rearrange this a bit into rows of 32-bit sections. And let's give each of these rows an ID. We'll use M0 to 15 to denote each of these 32-bit sections. And for the sake of ease, let's convert them into hexadecimal. These 16 values will act as the main input data, M. The next most important part of this puzzle is the initialization vectors. The initialization vectors are basically a 4-word buffer, each 32 bits long. It's represented by A, B, C, and D. Initially, the values of these 4 words are as follows. Later on, as we progress through the algorithm, each of these values will be replaced by something else. But for now, these values represent the 4-word buffers. Now, let's talk about the most important part of the algorithm. It's these 4 sections. Each of these are blocks of code that execute 16 times and perform various types of calculations. These calculations are intertwined and contribute towards the resulting hash. Let's zoom into the first one. Inside, we can see this complex series of steps. Don't worry if you don't understand anything. Let me explain. First are these 4 blocks labeled A, B, C, and D. These represent the 4-word buffers that we saw earlier. You don't need to understand the relationship between them right now. Just keep in mind that the values of each buffer gets replaced as the algorithm runs. Next comes our input in the form of M that we modified a bit earlier to fit the needs of the algorithm. The Ki here represents a constant value that's calculated using this formula here. We don't need to understand the formula, but here are the values that we need for our purpose. There are a total of 64 values of Ki that we need. Let's put this aside for now and talk about the heart of this whole operation, the if or the function block. The if or the function block is one of the hearts of the algorithm. There are a total of 4 functions in this whole algorithm, f, g, h, and I. Together, this is where the majority of the magic happens. Let me explain. F is a function. It takes B, C, and D as inputs and performs some bitwise operations on them. The operation it performs is this. Those who have taken Boolean algebra in high school should understand this. It basically says B and C or not B and D. Now, Boolean algebra deserves a full video of its own, so I won't go into the details. But if you want to know more, let me know and I'll consider making a video on this. Now, if we add the initial values of B, C, and D into the function and perform the calculations, we get this result back. which then proceeds to the next box. This symbol on the box represents modular addition. Modular addition is a bit different from the normal modular operations that you guys are familiar with. It uses this formula to calculate the result. Here, x is the initialization vector a, y is the result from the function f, and z is this. The value of z is equivalent to 2 to the power of 32, which ensures that the result of this operation is no more than 8 characters long. All the additions here are modular additions, so every time I say added, I mean modular additions. The result of the addition moves on to the next box, where it's added to a portion of the input message. Which input shall be added depends on the number of the operation being performed. Depending on that, a different message block will be added. Since this is the first operation, M0 will be added. After adding, it moves on to the next block to be added with the constant value of k. The I here represents the current number of operations being performed. Since it's the first operation, k1 will be added. For the next step, let's convert the result back into binary, because now we need to rotate the bits by a set amount. How many bits again depends on the number of operations being performed. But according to the RFC, for the first round, we need to shift it by 7 bits. It's basically taking the first 7 bits and adding them to the end. Now, with the bits rotated, it moves on to the next block. Here, it gets added to B. After that, it gets stored in the buffer B to be used as an initialization vector for the next operation. Not just that, all the initialization vectors move one place to the right, so D becomes A, B becomes C, and C becomes D. With the shift done, this whole thing counts as a one operation. These shifted values will be used for the next operation, at the end of which they will follow the same principle and shift one place to the right again. After about round 4, all the initial values of the buffer will have been replaced by values obtained throughout the process. This will continue for 16 operations. At the start of the 17th operation, we are done with the first stop block. The current values of the forward buffer will then move on to the next stop block, which looks exactly like the first one. And it is, except for a few small changes. First step is the function. Instead of the function f, we'll now be using function g. Function g looks something like this. Again, without too much details, it says B and D or C and not D. Second, while adding M, a certain sequence is followed instead of adding it chronologically like we did in the first block. The sequence will change during the next two blocks also. Here's the sequence. Third, when adding the values of k, the next 16 values will be used in its original order. So, k17 to 32 will be used. A predefined pattern is followed when shifting the bits. After the 32nd operation, instead of the g function, function h is used. A new sequence for m is followed. K33 to 48 is added into the mix. And a different pattern for bit shifting is followed. This remains true for the final round of 16 operations. The 64th operation proceeds like each of those before it. It uses the outputs of the 63rd operation as its initialization vectors for the I function. And it gives us new values for A, B, C, and D. After the 64th operation is done, the values of A, B, C, and D moves to the next block. As you can see, there are a bunch of symbols for modular additions. Here, the values of A, B, C, and D is added with the initial values of the buffer. That means these values again. The current values are added with the initial values. After that's done, we get the final values for A, B, C, and D. Now, we just need to concatenate them together and we have our final hash value. Pretty neat, right? Now, you may be wondering, well, what happens when the input data is greater than 512 bits? Well, if the input data is more than 512 bits, firstly, it will be split into multiple 512-bit blocks. Each of the blocks will contain 512 bits of data until all the data has been split into blocks. The final block must contain at least 1 bit of padding, plus the 64-bit length in binary. In case the remaining input data is exactly 448 bits long, a brand new block would be used just for the padding. The second last block would include the 448 bits of data, then a 1, followed by 63 zeros to make up the 512-bit block. Then the final block would contain 448 zeros followed by the 64-bit input length in binary. All of these blocks would now be processed in the main functions. Just like before, it would start with the 512-bit blocks and go through all the steps, using the output of the previous operations as the initialization vector for the next one, and it would be added to the initial input vectors in the last step before concatenation. But instead of concatenating them into a single string, the values of A, B, C, and D would return back to the top to act as the initialization vector for the next message block. This process would continue till all the blocks of data has been processed. After the final block is processed and we have the final values of A, B, C, and D, it would get concatenated and we would get the final hash value. Hashing is a really vital part in improving the security of our systems. Although it may seem like too much work, with hashing a little can go a long way. Well, that's all for today's video. I am starting a new series where I explain the inner workings of different hashing algorithms. So subscribe if you want to see more of this type of content, and a like would really let the algorithm know you like the video. Thanks for watching, and I'll see you on the next one.